For more information, please visit SGMAK Associates website.
Moving on, let's talk about a continuous random variable. In this case, because of the word continuous random variable, that means the random variable takes values, all possible values over one interval or more than one interval. We, instead of probability mass function, we call it probability density function. So in dealing with a discrete random variable, we define it as a PMF or call it PMF, probability mass function. In dealing with a continuous random variable, we define it as PDF, probability density function. A probability density function for a continuous random variable, f of x, must satisfy the following properties. F of x should be greater or equal to 0 for all values of x. And if you take the area under the curve uh, between the lower bound and upper bound of the random variable of interest, then that area should be equal to 1. Again, f of x should return a value greater or equal to 0 for all values of x, and area under the density function between the lower and upper bound of the random variable should always be equal to 1. The cumulative distribution function is given by the area under the curve from the lower bound up to a specific value of interest. So if I want to find out f of k, f is the CDF, then I have to take the integral of the PDF from the lower bound of the random variable to k. So area under the curve from lower bound up to that specific value of k represent that area represents the probability that the random variable takes values less equal k. And that's the basic definition of a CDF. Now, this is probability that a random variable takes values between a and b, two bounds. This is essentially what we try to solve when you solve a basic problem dealing with probability. I'll connect that with later on with examples later on, but that's the very generic question that you try to find out. For a given random variable that follows a known distribution, what is the probability the random variable takes values between a and b? Now, what I have shown here is both bounds are included. So probability x takes value between a and b, both a and b are included. Now, in terms of CDF, this probability is given by f of b minus f of a. That means you find the cumulative probability up to the value b, and you subtract the cumulative probability up to the value a. So basically, you're trying to find out the area under the curve, under the PDF, between the bounds b and a. Now, here's an important point to note. In case of a continuous random variable, if you want to find out the probability that it takes a specific value, as shown here, probability x takes a value k, a specific value k, that probability is always treated as equal to 0 for any value of x. Now remember, this is not true for a discrete random variable. The discrete random variable may have a probability attached to that particular value. So we can say that for a specific value, probability for a specific value for a continuous random variable is always equal to 0, but it's not true for a discrete random variable. Now, let's go to an example how to use CDF, PDF, and CDF for a continuous random variable to solve a problem. So here's a very well-known example. time to failure of an electronic component. So it has the following distribution, which is an exponential distribution. We'll talk about exponential distribution later on. So what you have is, given the PDF, f of t is beta is a parameter of the distribution, exponential minus beta t, defined for t greater or equals 0. So the random variable here measures time to failure. What you're interested to find out um, is what is the probability that the time to failure is over 100. So we use the CDF. From the PDF to CDF, the conversion comes out to be 1 minus exponential minus beta t. I'll attach a handwritten note just to show how you do that conversion from PDF to CDF. So f of 100 is 1 minus exponential of minus 100 beta. The parameter beta is the mean time between failure, average time between failure. And the probability that the failure occurs happens prior to the mean time is given by 0.618. That means whatever is the mean time for the electronic component, if the time to failure follows this particular distribution, then exponential happens to be exponential. Then the probability of a failure prior to the mean time is always about 62%. Again, let me emphasize that the basic equation that needs to be solved or answered is the estimation. What's the probability a random variable takes values between A and B for a specific problem? Now, here's another important point to remember. For a continuous random variable, the following relationship always hold. So if I'm trying to find out the probability x between A and B, both bounds included, that probability is the same if I drop one bound, one or the other, or both. So probability x lies between A and B, the same as probability x lies between less equal A and less equal B, or you drop the equality on one side. This is true for a continuous random variable simply because probability attached to a specific value for a random variable is always 0. Now, this is true for a discrete random variable only if probability x equal to A is 0 and probability x equal to B is 0. So you have to be careful just to make sure that these conditions are true before what you apply for continuous random variable can be applied to discrete random variable also. So so you have to pay attention to whether the endpoints are included in estimating the probability or not while dealing with a continuous discrete random variable. You don't have to worry about that for a continuous random variable.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.